Hi, everyone. I'm really looking forward to talking with you today. So the easiest way to think of Ethereum is it's kind of another system very similar to Bitcoin. And it has this one additional feature called smart contracts. Now, before I can really go in and explain exactly what smart contracts are, we kind of have to go a little bit deeper on what blockchain technology is. And so most of the stuff I'm going to be talking about, the first 2/3, are actually going to be exactly the same as in Bitcoin. And then when we get to the smart contracts, that's where things start getting a bit different. So now usually when people talk about Bitcoin or about blockchain technology, you hear this term, the financial ledger in the sky. It's sort of like this, we put all the records in some sort of place in the sky. Now, so to me, this explanation always is very confusing. For one thing, as Rumi was talking about earlier, there's this idea of the cloud. And so people wonder, what's the difference between the sky and the cloud? And in fact, blockchain really is very different than the sort of cloud that you're familiar with, where you might have data stored in an Amazon cloud. So this is a very different concept. The other problem with this definition is it doesn't really tell you anything about what the parts are that make Ethereum work. And so this is sort of like you're trying to explain to somebody what a beehive is without explaining what a bee is. Or you want to explain to somebody how the human body works and what it does, and you never mention cells. So clearly, this kind of, if we want to explain these things, the first place to start is let's talk about the individual pieces that make up the system. And so you don't really hear about that much with blockchain technology, and that's what we're going to be talking about right now. So I actually think the human body is, maybe because I'm a medical doctor, I don't know, I think it's a great way to think about blockchain technology. So the thing about the human body is it evolved in an extremely hostile environment, the surface of the Earth. And with Ethereum and other blockchain systems, they also grew up in a very hostile environment, which is the internet. And so there's a lot of similarities between these two systems. And in fact, they're both rather different than traditional computer systems. So if you look at a typical data center, so the computers that are in a data center, most of them are all descendants from the original IBM PC. And when you turn on the original IBM PC, you would get a C prompt. So what was missing on these early computers is any notion of security. So security was kind of tacked on later, and they were never designed with security first in mind originally. And so the way we deal with that in our data centers, having a little clicker trouble here. Oh, there we go. So the way we deal with this in our data centers is we put a firewall around all the computers, which works great, except if anybody finds a weak spot in the system, so a hacker gains access to a computer, they can usually create enormous damage across the data center. And this problem is even worse if you have somebody working for your company that has some sort of admin rights to the data center. You essentially have to trust that person 100% that they're not going to bring down your system, because they have that power. And every large company has many individuals in that company that have that kind of power. So if you're going to build a system that really places security first, you can't use this model of just putting everything inside of a shell. You have to come up with a different model, and that is essentially the model of how cells work. So the way cells work is every cell, as part of its job, has to worry about security. And otherwise, if you had a cut, you would get sick very quickly. But at every level of how the body is designed, you need an emphasis on security, or otherwise you can't build an organism out of billions of cells. And so I'm going to try to explain how blockchain systems handle security by thinking of them as cells. Now, I should mention that you can think of each cell in here as your computer running the Ethereum software or Bitcoin software. So when you start up your computer and you download a Bitcoin wallet or an Ethereum wallet, it's going to function like one of these cells, and it's going to take care of its own security. Now, let's think about what are the different parts of a cell. Well, obviously, the first part is the cell membrane. What is one of the main jobs of the cell membrane? It's to prevent poisons from getting into a cell. And of course, the internet is filled with poison. It's filled with poisonous information. And in particular, if we're dealing with some sort of financial network, the worst thing is some kind of poisonous transaction. So here we have this represents your computer. It's running as an Ethereum node in the Ethereum network, and we see a transaction go by. And now we have to decide, are we going to allow this transaction through the cell membrane into the cell? So we have to make this decision. So this transaction might say move 100 coins from one bank account to another bank account. So the first way that we can tell if this is poisonous is kind of obvious. We could just look at the transaction. Does it look like a good transaction? Now, this is exactly what the human body does with glucose. So there's cells, there's proteins on the surface of the cell membrane, and they can recognize the structure of a glucose molecule and let it in. And we're going to do the same thing with this transaction. So the other question you might have, though, is where does this transaction come from? Well, it comes from the neighboring nodes in the network. So when you fire up the Ethereum or Bitcoin software on your computer, it will randomly connect to somewhere around a dozen or a couple of dozen other computers in the world, and they're going to send transactions between each other. And that's how this mesh network is established. So let's look at the structure of an Ethereum transaction. It's actually very simple. It's just a little piece of data, and it has these parts in it. So it has a from address, who is it coming from, who is it going to, what is the value of the transaction, so how much money are we sending, and then some other more esoteric fields that we're going to talk about later. Now, the important thing is that the from and to, I have a little sort of marker there. These are addresses. So with Bitcoin and Ethereum, you have this concept of an address, and you can send somebody money from that address, or you can send money out of an address. So the first step to building a secure network like this is to simply make sure that all transactions we get have this structure, and if they don't, we reject them. Now, there's one other really cool thing we can do. The person who created this transaction, the owner of the from address, can add a little signature in there, and what that will, and only the creator or the owner of the from address can create that signature, and it guarantees that this entire transaction was not tampered with. Now, the important thing with this, so if you had talked to a scientist, computer scientist in the 60s, how would you create such a transaction, such a signature? They would have said it's impossible. But then in the 70s, within the CIA, they actually, what happened here? Oh, there we go. In the CIA, in the 70s, they came up with this technology called public key cryptography. And so in the 80s, if you asked a computer scientist, how would you create a signature like this? They would say it's easy. You can create a public key signature, which is what we've done here. So if the signature is correct and the transaction has the right structure, that means we can probably bring it into our cell. However, there's one other thing that we need to watch out for, and that is the fact that sometimes a chemical can be a poison, and other times it can be beneficial. An example of that is calcium. So if we have a cell needs to regulate how much calcium it has, and if it doesn't have enough, it lets it in. If it has too much, it doesn't let it in. And so in that situation, we have to look at context, and that lets us decide whether something that we're looking at is a poison or not. And so with a financial network built on blockchain technology, we have to do the same thing. And this by the way, so a cell has a much more complicated mechanism for controlling calcium concentrations. And that's why diabetes is a common problem, because cells can't handle glucose concentrations very well, but calcium is not so much of a problem. So when does context matter in a financial transaction? Well, one obvious example is we're sending money from one bank account to another bank account. We're sending 10 Ether. That would be like about $100. So obviously, this is a poison if the account that we're taking the money out of it doesn't have enough money. Because if we let that into our cell, then it's going to corrupt all our data if people can send more money than they actually own. So how can we tell this context-sensitive piece of information? Well, there's only one way we can do that. We have to look at the information stored inside of our cells. So we have this central area, which is a database, which stores a copy of the blockchain. What is a blockchain? It's very simple. It's just a list of every transaction that has happened so far since the inception of the network. And because computer hard drives are so cheap now, we can actually just keep a comprehensive record of all information for the blockchain. And now it's very easy for us to check if a particular bank account has a certain amount of money, because we just run through the transactions, and then it says, oh, there's $110 at the end in this account. And the important thing is this data never changes. It's completely immutable, but we can add new information down at the bottom. Okay, so that's one example of context-sensitive information we need to worry about. Another example that's very important is people may try to disrupt the network by flooding it with junk. So basically throwing spam transactions and trying to perform a denial of service attack against the system. So now with blockchains, they solve this in a very simple way. They simply require every transaction to have a fee. So if an attacker tries to do this, they would simply run out of money. Now that is still context sensitive, because we need to make sure they can actually pay for the fee before we let that transaction into our cell. And in order to do that, again, we have to scan the blockchain. Now, if all these things are true, then we can say that this transaction is not poisonous, and we can allow it into the cell, and now we can simply add it at the bottom of the blockchain. And that's how a blockchain is created. It's really super simple. Now, there's one thing I haven't talked about yet. There's one more attack that you can do that's really tough, and this is the one that wasn't figured out until 2008. And that is the fact that it could happen that there's two transactions at the same time going out of the same bank account that does not, and that bank account doesn't have enough to cover both of them, only one of them. And the money is being sent to two different locations. So this is called a double spend attack. We're trying to spend the same money in two places. So if we build this network of cells where these transactions are just floating around, it could be that some of the cells get the first transaction first, and some of the cells get the second transaction first. And so if that happens, everything will fall apart because our data will be corrupt. People won't agree where all this money is. So that's where the last context-sensitive piece of information that we need. We need a miner that will look at the very last transactions, and all they really do is guarantee the ordering of the transactions. So the node is responsible on its own deciding what transactions to bring in, but the miner says in what order they happen. That way we make sure everybody agrees that this first transaction should be valid and the second one should fail because there's not enough money. And so this is really the only role that mining plays in a blockchain system, but it's a very important role. Now, what we can do with this type of system is we can build a payment network that allows money to flow freely among these nodes. And we can do it in a way where we don't have to put the whole thing in a box. Every part of the network is responsible for its own security. And what we have now is a payment system that has two important properties. It's very reliable and it's very secure. And what's important is that it's secure and reliable from the perspective of a user. So if you take something like PayPal, so the PayPal data center at this point, I'm sure, is very reliable. And PayPal will say it's reliable. But for me as a user, PayPal isn't so reliable. You hear all the time where people get paid with PayPal and their account is frozen or they have hold periods of months. So that's not reliable for a user because, and it's fine for PayPal to do that, except there may be certain business models that you want to implement where it's not acceptable to have money sit and wait for multiple months. And the same thing is true for security. So if you were to look at the database servers for Facebook, their database will not have a login password with your name on it for modifying the database. Instead, the way it works is it uses two steps. It has an in-between computer that has access rights to the database, and it performs actions on your behalf. With this type of network, on the other hand, every individual user signs the transaction, and they're the ones that mutate the data directly without an intermediary. And so when you have this type of system, you can think of very quickly of all kinds of neat applications. So you might want to try to build something like a title registry for houses. You could do like a licensing system for continuing education, maybe something that tracks royalties on songs. But one of the problems you run into, and which is where smart contracts start coming into the picture, is in order to do any of these additional applications and run them on this payment system, you have to attach an old-style computer to the network. And this ruins all these advantages that I mentioned. So if I put in a machine there that runs a titling service, then that means the users have to trust that my computer is up. And if it's not, the system isn't going to be reliable. And similarly, when they want to move a title between two parties, they're going to have to ask me, the operator of that computer, to actually write into the database and make the change. So it's actually very unsatisfying as a developer when you start trying to figure out how you're going to build more interesting things than just payments on this. What we really want is we want this computer to also be a cell that runs the software for the blockchain system. And that's where smart contracts come in. So what we do with smart contracts is, it's actually kind of obvious how you would write a smart contract. There's really only one way you would do it. So here's our transactions. They're being added to the blockchain. So let's just create a special type of transaction. And what this transaction does is it has a piece of computer code in it. And so whoever submitted that transaction to the network can write a little computer program. And this is exactly what Ethereum does. And just like a human being, as I mentioned, humans that use these blockchain systems, they get addresses. This program also has an address, which is a little different. I put a little star in there. But what's cool now is once we have this program, later on, people can send transactions to that program. And in the to field, they simply put the address for that program. And so now we have a program, and we can actually perform function calls against that program over time. And so it might be that this is a title, an app that manages real estate titles. And that first red transaction says, this house should be moved to Lisa. And then the next one says, hi, I'm Lisa, and I'm now moving this title to John. And again, the from addresses would be from Lisa and the person who gave it to Lisa. So they sign and agree to this transaction directly at the user level. And the program can then keep track of how this title is moving around. And because it's a computer program with arbitrary computer code, you can make the rules as complicated as you want to that controls when and how a title may be transferred between two parties. Now, somebody else might come up with a program to handle royalties for music. So when somebody buys a song, it gives everybody a royalty. So this will run on the exact same system as the other one. These all happen at the same time. All the transactions are stored in the same place. So it basically means you're running a shared computer. And sometimes people describe Ethereum as sort of a shared computer in the sky. Now it doesn't have very high performance, but what you trade for the performance is you trade this reliability and the security and the ability to write computer programs that can send money around and can do so according to arbitrary rules and at arbitrary points in the future. Now, so you might ask, what can a smart program actually do? Well, a smart program can be called by creating transactions. And the other thing it can do is when you call it, it can generate new transactions. So it's a very primitive type of program. It's very much sandbox because, remember, this program is going to run on everybody's computer. And we have to make sure if it has any bugs that it doesn't crash the entire network. So it's very constrained, and it can only do two things. It can read in transactions, and it can spit out transactions. But the cool thing is that we can actually have many different apps working together. So maybe you're creating a title app, and you decide, oh, I don't want to use Ethereum as the currencies for title fees. I would rather use the US dollar. Well, there's already 3 different companies that supply a synthetic US dollar that you can use by calling, in this case, it would be the green program there, where you can basically send a transaction to another program on the blockchain saying, I would like to send 5 synthetic US dollars as a title fee. And then maybe the title app needs to know people's real name. Well, there might be another service that provides identity services, and there's already a couple of those. So now all of a sudden, you have these very secure apps, and you can link them together to solve more complicated problems in an ecosystem. So again, the goal here is we don't want to put everything in a wall. Everybody handles their own security, and we can build a system that has security at the level of the individual user. And we can, and by having being able to write computer code in this, we can solve lots of coordination problems that currently on traditional systems would be rather difficult. And so lots of different projects are being worked on that can run in this type of environment. And I really do believe that Ethereum and other systems like it are the first real native computing systems that are built with the internet in mind and the fact that it's a very hostile environment. All right, that's my presentation.